Let us compare properties that emerge from two different processes used in 3D printing with reactive materials. The first one is vat polymerization, where you have a liquid resin that is cured in a tank by sequential exposure of each slice. These are useful for making patterns for investment casting and can be scaled to large models. In contrast, we'll look at another process called material jetting, which is based on an inkjet based printing of photopolymerizable materials. And depending upon the proportion of the reagents that are mixed together, you can access a whole range of material properties. And you can also dial in multiple material properties in different locations. Let's take a look at what are the nature of the product that comes out from both those approaches. In this, you have a case where tensile strength is plotted as a function of a couple of different materials. In each case, a reported value on the right bar is compared to what was experimentally measured. You can see that there seem to be some minor variations between what was reported and what was measured in the lab, which indicative of the fact that depending upon the nuances of actual printing, you could have some variability in properties in the way it was printed and when the material was measured. You can also see that depending upon composition, you can have quite a bit of variation in properties from about 5% elongation to about 35% elongation. The materials on the left relate to material jetting. The materials on the right are indicative of vat polymerization. You also end up having flexural strength comparisons between the parts that are printed by the two different processes as a type of example. And in addition, there's a strength in the flexural modulus. Okay, so comparable material properties can be obtained. You can tend to get more of the elastomeric contributions and elastomeric formulations printed through the material jetting uh, method. Here's an example in terms of overall resolution. Was a demon head that was made by both methods. One thing that was portrayed was the material jetting method appeared to have a much finer resolution in detail than in the vat polymerization. When you compare these two materials, zoom into those regions, you can see that the process, standard vat polymerization process might give you resolution of about 5 mils, whereas you could go one order of magnitude almost lower in terms of layer thickness that's cured at a time um, by material jetting. And so that leads to much higher resolutions. And then here's an example of in terms of the overall sidewall detail that you can get through vat polymerization and a much higher resolution that is possible without warpage with the material jetting approach. Here's some schematic illustration of how you change the composition, you can get the properties by varying the relative amounts of the two reactive materials, two kinds of monomers in a polymerizable system. So for instance, here, if you wanted a softer material such as a casing for a mobile phone, you would go with a smaller amount of the rigid material. And as you keep increasing more of the rigid monomer, you begin to access a different property space and then correspondingly a much more different application space till the point where you get to very hard systems that are almost like ABS or polypropylene like that can be accessible through reactive polymer materials. Belt buckles, wheels for luggages, electrical insulation sockets. So to summarize, degree of cross-linking affects material properties. The degree of cross-link can be changed by process parameters. It can also be changed by chemistries. The influence of polymer structures and fillers also can be measured and dialed into material design to be able to get specific mechanical properties. A few material selection charts for design engineers are shown as to where polymer property space falls in context of the entire material space so that one can decide when to use reactive polymers for a given application as opposed to thermoplastics or based on modules 3 and 4, metals and ceramics. Key thing is AM processes and materials can be tailored for various applications by tailoring the property space. Let's see how all of this is put together in the next lecture, where we begin to talk about specific 3D printing processes that use reactive polymers.